Okay. Great. So yeah, thanks everyone again for tuning in. And this is a follow-up from yesterday's presentation. So apologies, I think I guess everyone except for maybe Christian was there. So sorry if not everything is super clear. But if you were at the journal club that I did kind of 2 weeks or a week and a half ago, then hopefully, yeah, most of this will make sense. But anyways, going to be looking at, yeah, kind of carrying on the discussion about view spheres and these preferred views and tying this in with this kind of motivating question of rotation invariance. And then that'll be kind of the first half. And then the second half, we'll look at kind of what do we do when we're sort of sampling points of the input space that are not familiar, that we don't have a learned representation for. And yeah, so for rotation variance, the kind of general approach that I'm describing isn't fully rotation invariant in the sense that you have to test multiple possibilities in order to kind of arrive at a solution. It doesn't automatically handle rotation invariance kind of perfectly. And I'll explain kind of maybe why to do that, and then how to kind of do this, but in an efficient way with basically some kind of heuristics, experience, and then also kind of how view spheres can help with this. And then I'm not really going to talk much about this, but just the kind of particle filters that have come up a few times. This could be a potentially useful way to kind of handle the sort of more brute force nature of this problem, just because particles can be parallelized quite easily.
So can I just ask about the particle filter things? I made a comment in Slack. I watched that video, and it struck me that in that video where they describe particle filters, it was very, very much like the union property we do in sparse representations. Have we talked about that before? Was that analogy been pointed out?
I think we have a little bit, not explicitly. Yeah, there's definitely analogies.
I mean, I just based it on what that video showed. I know nothing else about particle filters. But in that video, I'm saying that's exactly what we're doing with unions. You get these multiple hypotheses that are being basically active simultaneously. It's not a probability distribution, but it's multiple hypotheses, and they're being narrowed down through this movement, sensory movement experience.
Yeah, I think the one difference is you do need to be able to read out each particle separately to be able to do things. And
well, maybe that's the way they implement it in particle filters, but
right.
But in the union, you do them simultaneously because of the union because of sparse properties.
Right.
But other than that, it's basically the same hypothesis. You have multiple possibilities are being narrowed down through continued inputs. I just thought, wow, that is exactly what we do in the temporal memory. It's striking to me. Anyway.
Don't they also resample around the most likely ones?
Yeah, they do, but I mean, those are details, right?
Yeah, some of those would be. That's what I meant. Some of that kind of thing is hard to do with unions because you can't read out each pattern independently. But there may be ways of doing something equivalent with unions.
Right. I mean, I assume that in the particle filters are like these are probably I don't know, some floating point numbers, and they're very precise, and so you have to resample or something. I don't know, but so there are those differences, but the idea that you've got multiple hypotheses active at once, and you can start out with a lot of them, and then you just get narrowing down, and you're doing them in parallel. Maybe in the actual particle filter code, they do them one at a time, but theoretically they're being done in parallel, and that's what unions are doing. And the fact that the union is not a distribution in the sense of a normal probability distribution, it's multiple hypotheses. Anyway, the language in that video was very clear video, and it was simple, but the language was like, wow, that's very, very similar to temporal memory. Anyway, I thought that was good, so just wanted to point that out before we go on here.
Yeah, no, yeah, and I mean, I think Marcus at least has discussed some of the similarities, at least when I've spoken to him, and I think in the Columns Plus paper, he has a paragraph about the similarities. But
is that right? Yeah, that's funny. I don't remember that.
I've posted on Slack, I think in the thread, but yeah, but I think it could be helpful because there may be some. It's still unclear, but there may be some very efficient libraries for particle filters that we could use, and that might be just an alternative.
Or either, temporal memory could be an efficient method for particle filters. I mean, it's like, that's an efficient mechanism for doing it, if you could combine those two. All right, I just want to point out brute force sounds like it's not desirable, but when I thought about, hey, temporal memory does this, and it can be very, very efficient, I think. So anyway, I just want to mention that.
So kind of why even debate whether we want to, like, maybe on some level you'd think surely we want to find some elegant, perfectly rotation invariant representation of objects, but in general, invariance comes at some sort of cost and sensitivity. So a classic example of this is max pooling in CNNs reduces the kind of spatial sensitivity of a feature representation, which helps with translation invariance, but it also coarsens the spatial code of features and potentially makes them have these kind of undesirable properties, like being kind of approximately bag of feature detectors and so forth. And so I thought, well, if humans seem to use kind of a search-based solution, or at least semi kind of search-based solution, rather than kind of solving this test perfectly, then that might represent the fact that biology has found it to be a good trade-off. And then that way we can focus on the representations being able to handle other equally challenging invariances like translation, scale, and just novel examples of objects. So this isn't a new idea. The kind of one obvious thing to do is to just test the most likely orientations when you come across an object. But just to kind of get into this a bit more, so most likely can be a combination of experience as well as some heuristics based on local features that I'll get into. And in order to kind of talk about this, what I'm going to kind of loosely define it is principal axis of an object. And so every object will have this, and it basically is just with reference to how the object is normally placed in the world due to the constraints of, for example, gravity. So a coffee cup. And it doesn't specify rotation around the principal axis. So coffee cup can obviously be oriented around that in various ways, but at least the principal axis tells us if it's right way up, upside down, or on its side, or in some kind of more implausible orientation like this. And as you'd imagine with experience, you'd come to learn that some of these are more likely than others. And so should be tested. It should form a kind of denser part of the distribution over possible rotations. And interestingly, humans do seem to do something like this. So this is a study where they looked at how quickly people are able to recognize. So this was just line drawing, so 2D images of things like airplanes and boats that were oriented in the plane at various angles. And so this is how quickly people recognize it. So lower down is faster, is better. And so at kind of an upright, typical orientation, people are very fast. They're able to tolerate slight deviations from this. And of course, if you turn it completely upside down, then people are much slower. What's kind of interesting, though, is that the kind of worst ones are these kind of deviations from this. So like upside down seems to be better than upside down and slightly skewed. And similarly, being at 90 degrees seems to be better than these slight deviations from that. So that does kind of suggest that, yeah, we might have these sort of non-uniform priors over what the kind of typical orientations of objects in the world are. When we're trying to recognize something, we're kind of parsing through this feature space and testing hypotheses with greater likelihood that correspond to these kind of more common orientations. But of course, sometimes the object won't be in its typical orientation, and it'd be nice to have some other way to kind of constrain the hypothesis space and make it faster. So one thing I was thinking was that the kind of local features, in particular principal curvature, can give us some information, some sense potentially of the kind of orientation. So, but essentially a flat surface will generally be, or often be in objects either parallel or perpendicular to this kind of principal axis, often because it represents the base or because it represents kind of the side of some object. Obviously, this does not always hold. If you had a polyhedral dice or something, there's many examples where this doesn't hold, but this could, as I'll get into a bit more concretely, be one way to kind of suggest, okay, the axis might be in one of these directions. And even if the local feature and the principal axes aren't flat, they give us, the principal curvature isn't flat. It gives us the maximal and minimal curvature. And one of these is also, again, typically oriented, so either parallel or perpendicular to this principal axis. Because
Yes, are you defining this principal axis with respect to gravity purely?
Essentially, yeah.
Yeah, because this cucumber or whatever it is, you could argue the principal axis is actually, almost horizontal. It's sort of along the.
Yeah, and I mean, I haven't decided for sure if that's the best way to do it, but I think, but in general, it doesn't matter too much in the sense that normally, if the principal axis isn't like that way, it's going to be that way. It's, if you see what I mean, it's not going to be any of the kind of angles in between.
Right.
But when I was thinking about it, I thought just a natural way of defining it, because you can have very kind of asymmetrical objects and things like that. So actually, maybe just a natural way of defining it would be, when you encounter this object in the environment, what is its most typical orientation?
Yeah, in some ways, it's simpler than thinking of it as sort of shape-based. If it's more gravity-based,
exactly. And because the problem is, if it's shape-based, you kind of, at some point, you have to decide. You kind of then have to first learn, okay, what is the shape of the object,
right,
and then decide, and how you kind of parse that, and so then bringing all this back to view spheres, the idea is then, for a view sphere like this teapot, you have the features are on this view sphere relative to kind of the learned principal axis. And when you're inferring an object, of course, it can be at any orientation in the natural world. So you need to not only infer where you are on the object, as in where you are on the view sphere, but also what the orientation of the object is that you're actually studying. And so this can also be conceptualized as a sphere, where the point on the sphere is basically, if you take the principal axis out of the object, it's pointing to wherever it is oriented on the sphere surface. And so this is just a single example of a orientation hypothesis that you might have. And so what this means then is, for example, if you were to see a feature, and the idea is you would have multiple hypotheses that you're running in parallel about this orientation. So this is what I mean, that it's kind of search-based.
So you're just testing along one axis, so you don't represent rotation like around.
Yeah, so exactly. So I'll get to orientation, because if you have an estimate of the principal axis, of course that estimate may be wrong, but let's say this is one of your hypotheses, the first one, and this is another one. If you see a spout, that tells you essentially what the rotation is about the principal axis, because and this is kind of one of the, I guess, benefits of the view spheres, because you can only see a feature from one particular side. Then as long as you have kind of an estimate of the axis, which again could be wrong, then seeing a feature is going to give you some information about the rotation about the axis.
But isn't that the same problem as the whole object? I'm looking at the spout. I have to figure out the orientation of the spout.
So I'm assuming here that the spout representation. So if the spout representation tells you some information about orientation as well, as in like whether the spout itself is upside down or right side up, just gives more information and makes it easier.
Right.
I'm assuming that the spout representation is invariant to rotation.
But why would it be? I mean, it seems a spout is just another object, and it seems that's the same problem as the whole copy, the whole teapot. It's like I have to figure out what the spout is.
Yeah, that's I mean a fair point. I guess I was imagining, yeah, kind of a local feature detector that could recognize these things from, yeah, because it's, I guess, a smaller feature. Generally, simpler features you've encountered more often in the environment, and so you'll have encountered at more orientation. So this would be more dependent on training-based.
I'm not sure I buy that.
It's sort of what I was saying yesterday. I think you have to assume this is in some sort of a hierarchy or multiple cortical columns, and every cortical column is doing this. So you might have a cortical column that knows about spouts and it's doing the exact same thing, but at the level of the spout.
Yeah.
And then you have a higher level, maybe a V4 IT or something like that, that's operating at the level of the full.
Maybe. I don't know.
But it's the same operation. It's the
I don't
same
know.
thing.
It may be. I think, but the problem is, I think it has to occur at each column. Or right.
Yeah.
See, whatever it is, we don't want to rely on hierarchy. But the point is, that spout is not really easily recognized. In fact, if I isolated it from the teapot in this view, I'm not sure I'd figure out what it is. So it's certainly not like, oh, there's an oriented spout. They already know the orientation of the whole thing. It's I don't think so.
Yeah, I think if you isolate the spout rotated 180 degrees, you wouldn't be able to recognize.
Well, even in this picture, I don't think I'd be able to recognize it there at all. It's if I just had to isolate the spout. Anyway, I guess. I mean, you can make a hypothesis based on the symmetry of that image. That would work, you know, or there's sort of an implied principal axis of the symmetry of that image. But I don't think I could get it from the spout.
I'm not sure this is a problem because, again, you have lots of cortical columns at different scales that are operating together and voting on things, and the only self-consistent view is this thing.
Well, all right. So you're saying orientation would be voted on, and
I'm assuming that,
but
because you have multiple hypotheses for orientations.
Yeah, but we still have to ask where each column's hypothesis is generated. Everybody's rotated here, so all inputs are rotated. So everyone would be confused. Everyone has to solve. I don't know.
Yeah, I think
It's
I think at some level
happen.
I'm approaching it from. Sorry.
Yeah, but that gets back. It's not like it happens instantly. It happens over time because these unusual orientations do take time, as Niels showed earlier. So there is some sort of a search process or settling process.
Well, there's two different things. One is the brain could literally be trying different orientations. You could still be voting on it, but you might be going through them serially as opposed to, oh, there's this distribution of orientations and the right one comes out.
Right.
That doesn't seem right to me. It's more like it seems like because it takes longer. It's not just a voting thing. It seems like there might be, like you might be doing multiple orientations.
But yeah, it can still take longer, even if you're doing trying multiple orientations.
Or it could be both. This could be some combination.
Yeah, it could be a combination.
Yeah.
I would agree that there is some voting and settling going on, but it still seems like it wouldn't be like, oh, some of these guys have got it right from the beginning. Everyone's going to be confused by this. It's a pretty confusing image, you know.
Yeah, I guess that would be part of this if we go down this road of testing some of this stuff out. How would this happen in parallel across cortical columns, and how would it settle? It seemed like it's plausible.
What is plausible?
That multiple cortical columns could figure out these unusual.
Yeah, but are you saying that some of them guessed right to begin with and they went out, or are you saying?
Or eventually it will guess right. It could be some combination of parallel.
Right. I think it seems to me that it has to become a combination.
Yeah.
If I look at this teapot, and introspection is only worth so much. And I said, well, what really clued me in on what the orientation is teapot? I think it's a little knob on the top. That piece itself is kind of, it's got more shape to it than the other stuffs. And I focused in on that one. Like the spout itself is very confusing. It's like,
and I agree. Also, like where it touches the table.
Is it touching the table?
Yeah.
I don't see a table. There's a
The
table.
table's on the top right.
I don't see it. Is there,
Paper
I
surface.
don't see a table.
Yeah, I see it.
There's a subtle shadow there.
Oh,
The
boy,
brownish.
that's pretty simple. I didn't see that at all. I just saw the teapot floating in
Yeah.
space.
Yeah, interesting.
Um,
And then
I mean,
also,
yeah, it's difficult when obviously because also here we're looking at the whole object. I mean, at once and how well we would do this. I mean, because all these kind of tasks looking at people kind of recognizing objects at weird orientations, that is showing the object in its entirety at once. It's not requiring that they kind of saccade over a tiny.
But are they able to saccade, or they just like get a flash image?
I'm assuming they're able to saccade because
How much time is involved here?
yeah,
That-
actually
quite a bit of
no,
time there.
not in this case. Yeah,
That's
because
100
here they were.
milliseconds?
Yeah, exactly. So
That's not
here they're
fast.
responding very quickly.
That's not fast enough. Just the kind of-
But so they're basically processing it in parallel, and so that's of course going to give additional signals about orientation of an object.
also my subjective experience based on introspection is, if I look at this thing, I feel like I like to rotate it. It feels more comfortable.
Yeah, but why? That's why. That's the question, right?
Yeah.
Why does it feel like you want to rotate?
Yeah.
I mean, there is an implied principal axis in that image, symmetry, and that would imply that it's not right.
It's implied principal access and boundaries of the image itself, so.
Yeah, the way it's cut.
That is true. I was trying to ignore that. I was assuming that wasn't part of the test here.
You may better cut the images around. Doesn't give away the orientation.
But in 100 milliseconds, you don't really get a chance to do much at all.
Yeah, the maximum like 2 seconds. Like
Not even,
2 seconds.
I don't think. I mean, you typically get 3 to 5 in a second. And so I don't think in 100 milliseconds, you would not be able to do it in a saccade. It would be just one presentation. Interesting. I don't know. Okay. Yeah.
But anyways, but so I guess the whole desire or kind of motivation for this is that the hope is that potentially one of the benefits of the view sphere may be that it reduces the degrees of freedom of testing orientations of the object, because I said, in this case where you're getting a sensation which in the reference frame of the view sphere is along the side, then you just have to test all the hypotheses about the orientation of the principal axis. You know where you are with respect to around the principal axis. If you, on your first sensation, you experience the lid, then you need to test all the hypotheses about the orientation about the principal axis. But you know the orientation of the principal axis because it's pointing at you, if that makes sense. And then if you test somewhere in between, kind of along kind of these surfaces, then you generally get more information about both, because you'll get some information about the principal, assuming that features are not symmetric on every surface. If features are symmetric on every surface, then it's the typical issue of just you'll have to test for all the different features that coincide with that. But at least this constrains or should constrain the number of orientations that you have to test. This example where you kind of first feel its spout and you have, for example, these two hypotheses, and then you rotate the object like that. With one hypothesis, you then see flat, which is inconsistent with the other hypothesis. You see the lid, and then so you know that principal axis was the correct one. And it's just the standard idea. But so I think this would then basically help limit the total degrees of freedom of pose and of both location on the view sphere and orientation of the object. So the kind of general pose to 4 degrees of freedom, which are basically the azimuth and the elevation on the view sphere, and then the azimuth and elevation of the either the principal axis or the orthogonal axis, whichever it is that you're trying to work out, depending on what you first started feeling.
I'm lost now.
Okay.
We're trying to figure out the orientation of the object, and you're saying you're limiting it now to 4 degrees of freedom, but that seems like a lot. I typically think of orientation as 3 degrees of freedom.
So 4 degrees of freedom
here?
also includes on where you are on the object. So it would be 6 degrees of freedom if you
I
were
see.
both the orientation of the object and where you are in XYZ space.
But if I just think of the object as a whole, not like what part I'm focused on, its orientation.
So orientation is only 2 degrees of freedom.
Well, that's
Well, okay, I mean,
no,
yeah,
it's three, right?
I guess it kind of bundles them together.
Yeah.
You get a coarse orientation with 2 degrees of freedom. You get full description as of the orientation as well as where you are on the object.
I mean, in general, just to be clear, make sure I'm thinking straight here. General orientation is in 3D is 3 degrees of freedom, right?
Yeah.
And then your location is 3 degrees of freedom.
Yeah. So this is trying to do both with in total fewer, but yeah, it's a fair point that you're having to describe orientation with, if that's all you cared about, then yeah, it's using more degrees of
This
freedom.
assumes you're centered on the object somehow, right?
Yeah, that you're like kind of holding it at I guess a fairly frequent or common distance.
Well,
That's what you mean.
I mean, if I have multiple,
Actually, the distance hopefully doesn't necessarily matter so much. It's more that you're kind of rotating it consistently with respect to your eye. You're not kind of moving it all over the place.
well, if I'm presenting this to the eye all at once in a flash, and we have to assume that there's voting going on. There's multiple models trying to model this at once. Otherwise, I'd have to think of it like, oh, I can only see a small part of the object, like through a straw, in which I'd have to move my eye. So we're looking at a situation where you have multiple models, multiple columns, each sampling the object at different places. They have to vote to reach a consensus. They're not going to, in this 100 millisecond example, there's no saccading going on. I'm just stating things I think are facts in this situation. I'm not drawing any conclusions from it. Interesting.
Yeah, I mean,
I think so. This won't be able to tell. This doesn't say anything about rotations about the principal axis, right? That's the degree of freedom. Is that true? That's what's missing here.
So that's what comes with the view sphere.
With the position, it comes with the position of the view sphere.
Yeah, the position on the view sphere.
Yeah.
Right. It's because we've taken this complex object and flattened it out to a sphere.
Right.
Yeah, and you can only move along the surface.
Right.
Yeah, I mean, doing this without movement isn't something I've I'm assuming at this point that this is being solved by rotating the object.
Right.
I haven't approached this with the idea of how to do this with flash inference.
Right.
Okay, well, but that earlier experimental data was with flash inference.
Right. I mean, yeah, I'd have to double check because that could have, for example, been a corrected estimate of how long it takes them to respond, as opposed to how long the stimulus was presented for. Like it could have been presented.
I assume that was how long it took them to respond. That was my assumption.
Okay.
So
After stimulus onset.
yeah, they flash an image, and how quickly can you push the button, or identify it or something?
No, there has to be an offset because you can't have 0.
Yeah.
Oh,
So
there's
the
some
shortest
base reaction
time that a
time and
person
then
can
plus.
pursue something is like 60 milliseconds.
Could you show it again?
I mean,
It has to be, if you're basically going to do a button press or whatever it is.
Okay, it is stimulus duration. It means stimulus duration.
Oh, it's stimulus
So it's very quick.
duration. So what does that mean? That means like,
How do you measure it?
this means like, if the stimulus presented shorter period of time than this, you wouldn't be able to recognize it? Is that what that means? This is the time it takes to which you can then recognize the object?
up to some accuracy level, probably.
Yeah, exactly. Probably something like that. I'd need to look again to be sure.
Yeah.
Okay.
But yeah, it'd be something like that.
So just to be clear, is the response identification of the object or identification of the orientation of the object?
The object.
Okay, so you could presumably, assuming that there's some peripheral vision involved rather than it's purely foveated vision, you might get a general impression.
Exactly. Yeah.
Yeah, you're gonna get the whole image, the whole thing's gonna be presented to you, so.
Right, but I mean, but I'm going to assume that a soda straw is just not enough to solve this problem.
Right.
That's the whole thing.
It has to be involving voting of some sort, otherwise you can't, because you can't do it with the straw, therefore, you know, and we're not moving the eyes, because this is a stimulus presentation. You don't have the option to move the eyes in this period of time. Okay.
But yeah, basically, what I'm trying to get across is that it may be that so they kind of the first stuff I discussed about kind of testing most likely orientations and heuristics, that's kind of more general, that isn't specific to the view sphere. But yeah, what I was just trying to get across was that it may be that if we adopt this approach, we can reduce the degrees of freedom that basically need to be considered, which can make the system faster, no matter how it's implemented. And this is just kind of hopefully making it a bit clearer, kind of how you can test with this kind of probability distribution, for example, with particles, where initially you might have this prior that the principal axis is either at the kind of upright or inverted or on its side, which is kind of anywhere along the equator. But then, for example, you get a sensed kind of curvature feature, which has the principal curvatures oriented like this. And so that gives you some low evidence that the principal axis might be actually oriented like that, or I forgot to include it there, or kind of around that equator. And then you just kind of update your sampling based on that.
Niels, just one thing about, because when we went to the four-dimensional thing, are you assuming it's possible for the principal axis to be pointing head on at you?
Yeah, that's what I was saying, that if that's what happens, then what you need to, then exactly what the principal axis is, because the feature you're seeing is associated with the exact direction of the principal axis. But then you need to test the orientation about the principal axis.
Well, if the principal axis is head on to you, you don't have any features in line with it to validate it.
What do you mean? So so in this case, it would be the lid.
Right. If you're looking directly at the lid, okay, you may or may not have enough information. I'm assuming there's more information if the principal axis is somehow parallel to the plane of vision rather than perpendicular to it. So if that was the case, then
is that true?
What do you mean about more information, sorry?
Well, if you're used to seeing the object with the principal axis vertical, okay?
Yeah.
It's not perpendicular to you, right?
Yeah.
It's parallel to the plane of view. So that's if you wish, your most common viewing position with gravity obtaining and you're coming in from the side.
Right.
So it takes a little bit of mental leisure to me to say, if all of a sudden I've not seen the thing from the top, and all of a sudden I'm being shown the picture with the lid being the foremost thing, it might take a little bit more effort to actually recognize that, because the principal axis is now head on, and all the features that we've seen so far have been oriented with respect.
Well, it might be. Well, isn't that the same as saying if I'm seeing the object from a viewpoint, I've never seen it before, I may not be able to recognize it at all, right? It's because I just never seen it from that direction, or
potentially. But I guess
but this would also,
it's not the most common.
Yeah, but the most common means I haven't seen it very often. It may or may not have a lot of features. For example, if I look at the bottom of a car, there's a lot of stuff there that could identify the bottom of a car, but unless you spend some time underneath cars, you may not recognize it at all.
Right. Where I'm trying to head with this is that if if the capability of recognizing the principal axis is only one-dimensional, in other words, it's rotation in the plane, that still gives you a lot of affordance in trying to figure out what the object is. It takes, in my mind, if you're allowing the principal axis to come out of the plane of the viewing direction, you're asking a lot more of the system. But
But
you might be
I mean,
able to get
you
away
would
with
expect
just
it
one
to be
dimension of the
slower.
principal axis.
So yeah, with this approach, you would expect it to be slower if the principal axis is coming out of the image at the eye.
By definition, if that's the case, then you're looking at an uncommon view, by definition, right?
Right. So I'm saying that you might get away in a lot of situations with just having one dimension on the principal axis. Identifying that is going to be a somewhat easier task than the case where it's foreshortened in your.
Right, it would be.
But yeah, I mean, it'll definitely be easier, and that would be preferable. But of course, I mean, there's going to be the possibility that the object will be oriented that way.
There's a possibility, but it might be, you might bring other mechanisms to bear to resolve that. In other words, you might not be able to do it in a flash recognition, but you might be able to do it some secondary mechanism.
Okay. Yeah, I see what you're saying. Yeah. So just you basically consider, yeah, whether it needs some other kind of step involved when that happens.
Yeah, there are definitely times I can easily imagine situations where a flash inference is not going to work, and then you have to start attending the different features and figuring out what those features are. And but there's other times where you can do it in flash inference at different orientations. So it seems, as we were saying earlier, it's kind of a combination of both, right? There are times when you have to break apart the system and attend to different components. Other times you don't have to.
Yeah, I mean, I'm actually, in some ways, I'm surprised by how well this works, because I mean, there's classic examples that, for example, distinguishing T's and L's and recognizing those in periphery with very short presentation times. If the T's and the L's are kind of oriented right side up, kind of the familiar orientation, then you can do that pretty attentively and very quickly. But if they're skewed at 45-degree angles, then you can't.
So what, you're fixing at a point, your fixation at a point, and they show it in the periphery, and you have to recognize it? Okay.
Yeah. And basically, yeah. So there is an effect of kind of the familiarity of an object and being able to kind of in parallel process it.
Interesting. What puzzles me about this experiment you've shown is if there's some mental process going on, it takes longer if it's at an angle. Why does it matter how long it's presented on screen? Because what you show here on the y-axis is the presentation time.
Because what they typically do is, I think that's probably what happened here, is once the stimulus is gone, they mask it with some random dots or some mask thing, and that wipes out your processing completely.
Right.
So it's not like the image is gone and you can still think about it in your V1 and V2. It's like they show a mask.
Your mind's eye has been disrupted.
Yeah.
Right.
So I imagine I'm not sure.
That's typically what they do.
Yeah.
That would explain. Otherwise, you're right. You can just sort of keep imagining
playing it. Yeah.
It's interesting. You can even do that, which is interesting. Like, right, so where is that image resided? Where, like, I guess the cells keep firing or something.
Yeah.
But they keep firing in a way that if I didn't mask it, they keep firing in a way that I can mentally manipulate still. So it's like you've got this impression, but somehow I'm still able to manipulate that, even though I'm not getting it. It's like if you try to think of the neural mechanisms for that, it's kind of weird.
To visualize things too when there's no stimulus at all. So there is some circuitry for doing. Presumably both they did their common.
I mean, that experiment is pretty consistent with that idea we presented a couple of months ago, where you have each cortical column maybe having a few different orientations that it's exploring in parallel, and different cortical columns have different orientations, and they sort of together figure out which is the best one without any additional sensory input.
Yeah, and if you just have more cortical columns representing the more likely orientations, then it's
Yeah.
more likely that those will converge quicker.
Yeah.
Yeah, so just the kind of last thing to say on the rotation invariance is just that one thing I have an interest is kind of how do you actually learn the principal axis? I mean, I mentioned that it was kind of relative to how the object normally sits in the environment. But yeah, I mean, I was talking to Subutai about this the other day, and yeah, he was kind of suggesting maybe there's something where we can kind of initialize it randomly and then yeah, iteratively update this, and whether that's something to do with the kind of frequency of encountered orientations or something along those.
Although I think,
But,
you know, the way you phrase it as being sort of dependent on gravity makes it actually easier. It's not making it shape-based is a little bit trickier, I think.
Yeah. Yeah, I think the gravity would definitely be a good
What do you
starting
think?
point.
You just assume that the thing is, your first impression, you just assume the thing's oriented vertically relative to gravity, is that what you're saying?
That would happen most of the time.
Yeah, right.
I mean, some of
Yeah.
the time you might see this first time on its angle, but very likely the first time you see it, it's oriented in a natural way if it's
Right.
gravity based.
Yeah.
And if you, yeah, I'm assuming that over multiple sessions you would encounter an object. You wouldn't necessarily. I mean, I suppose your principal axis on the, if the first time you encountered it, if at some weird angle, then maybe your principal axis is initialized at that angle, but that it could be updated as a more common orientation
Yeah.
Yeah.
itself.
Yeah.
But we typically,
Yeah, and
you know, learn through the world. We experience things multiple times. Even a single time I'll hold something, move it around, or, you know, it seems, it's hard to imagine, oh, I only saw the coffee cup once and it was at this weird angle. I never saw it again, or I didn't manipulate it when it was like that. It's something like
But in the columns paper and column stuff, we just randomly did it in the very beginning, and then we never updated it, even if
Randy
So we-
what at the beginning.
the anchoring, the orientation, the object's reference frame,
The object reference,
Yeah.
yeah.
including orientation, sort of randomly initialized.
Yeah, yeah. But I mean, that's a subtlety of, well, we didn't even do orientation in the columns paper. We just did anchoring the grid cells. We assumed the orientation, we always assumed the orientation was the same, right? We just,
Yeah.
we didn't really solve a bunch of these problems.
yeah,
I think
like
it's
in
an
the,
interesting exercise to think of this without movement, just as a flash of, like, that forces you to think about the voting and
Yeah, right.
a little bit. And I guess on the flip side, it also has to work with just a single cortical column,
With movement,
move with movement. It has to work in both scenarios.
yeah. Yeah,
It's the same, it's just sort of voting in parallel or voting over time. It's the same thing.
no,
yeah, it's still not clear to me, and maybe this is just a misunderstanding of mine, but how voting really deals with the spatial arrangement of the columns, because generally, I feel like from my understanding, that's the key difference, is that generally with the obviously with inference, you're doing path integration, and so you're taking account of the spatial arrangement of features, whereas with voting, it's more about, okay, what is the hypothesis at this location, this location, this location. But when the voting is taking place, the columns don't have any sense of where they are relative to one another.
yeah, and they need
No,
to.
they would.
They need to. We didn't show that in any of our papers, right?
No, but we talked about it in Monty. Every
Yeah.
column has the position of the sensor relative to the body and this sort of.
Okay, so
three
that
vectors.
is still being accounted for.
That's
Okay.
been, yeah.
Yeah.
Okay, cool. That
I-
makes more sense.
I even had it, even in the 1,000 Brains book I wrote about
Right.
this. I was saying it's like these little agents in the town, but now the agents know where they are relative.
Oh yeah, okay, I remember that bit actually. Yeah.
Yeah. I don't think we never implemented this. I don't think.
Right.
No, but it is a core piece of Monty.
Yeah.
Every module,
Yeah.
every cortical column knows its position relative to the body at
Yeah.
all
Right.
times.
Yeah, because otherwise it's just going to become another bag of features.
Right.
Exactly.
So.
Yeah, and this allows it to work, you know, whether it's touch plus vision or, you know, one cortical, one visual field versus another visual area, it all works out
In theory.
in theory. It kind of has, I mean, you're estimating, at the end of the day, you're estimating the orientation, the pose of the object relative to the body. And you know the pose of the sensor relative to the body, and now you just have to figure out the pose, you know, and you know, you have the pose of the sensor relative to the object. Those are the three quantities that you're working with always.
In terms of, just random again, I'm just thinking out loud, so just hope you don't mind. I keep coming back to this idea that there's a really good chance in my mind that this orientation, a good portion of the orientation is being handled in the thalamus. And one of the things about the thalamus is it is a way for many large areas of the cortex to be processed at once, because it's all close together there. It's not as distributed, like you have this large area V1, but the equivalent processing center in the thalamus is close enough and they can all be connected directly. And so that would imply somehow that the orientation resolution is being done, it's being applied equal to all the columns. It's not like each column is independently solving the orientation. It's sort of like they're solving it together. You can have multiple. You can have multiple hypotheses, but only one can be tested at a time, something like that.
Right.
I'm just again thinking out loud.
Yeah, and we thought about the processing speed of the thalamus. It seems like it should be all at the same time, right?
But it's
a
just
specific orientations.
I wasn't thinking about speed. I was just thinking in terms of, the thalamus is a way of it's like one of the questions I've already asked is why is the thalamus, why, if it's, many people think of it as sort of an extension of the cortex, but why isn't it distributed throughout the cortex? One of the reasons is if you bring it all together, then you can do a simultaneous process that affects everybody.
Mhm.
And so all the columns, it's a way of applying something quickly to all the columns. So again, it just suggests that it would suggest that the individual columns aren't independently trying out different hypotheses about orientation. There's going to be a single attempt that applies to everyone. If that doesn't work, there's going to be another one. It sort of goes away from the classic voting on orientation, more towards like it's going to be, everyone can contribute, I guess, but the thalamus is going to try one. It's not going to have multiple hypotheses going on at the same time.
The paper I read, and it might have been less for anatomy or hypothesis, but the notion was that in the LGN that a certain amount of edge detection was going on. Does that correspond to your thinking?
No, that's not related to what I was just saying.
Well, I'm going to make a relation, but I'm just asking, is that the case in your knowledge?
No, actually, it's not the case in my knowledge. I wouldn't be surprised if someone made that claim. It seems like someone makes a claim about everything. But the general view is still that, well, it depends on the animal. I'll take that back. I think they've discovered that in some animals. But in primate B1 or even, I believe they have not seen that. So I think that was true like for rodents or something like that. But in primate B1, like a monkey, or I think even cats, they don't see that. They see only center surround response properties.
Okay, because there's the paper kind of went on to kind of, it was more image processing, but the notion would be that you could come up with the notion of orientation by voting on the number of edges in a particular orientation.
Yeah. Well, I think in general in primate vision you don't have that. You can't. It's just center surround, and I just don't appear until you get the cup until you get the portrait. Okay. I think it's a pretty solid result.
It'll be a nice voting result. I mean,
yeah, I don't see the thalamus as voting necessarily, I suppose, but it seems that
I don't think the thalamus could vote.
Yeah, it's more like it's just doing a transform on the input. And
no, I agree. I was not saying the voting was occurring there. I was saying they're producing inputs that could be voted.
Well, you can produce the edge in the thalamus. You can produce the edge in the retina. You can produce the edge in the cortex.
But if you're trying to center the notion of orientation somehow, like the thalamus, if they're basically,
I think as what I'm saying is the thalamus could it seems capable of our hypothesis that it would be able to reorient the input and in a sense give you a chance to try it out. Say, hey, what if I rotate this thing 30 degrees? And then the cortex looks at it and says, oh, now it looks normal, right? It's more of an a deorientation mechanism than it would be a voting or something.
but we don't have necessarily a mechanism for what hypotheses can produce.
Well, right, the cortex would have to provide those because it's through the feedback.
Okay.
Right.
Okay. Got it.
Yeah, I'm always struck, and I've meant this many times before, is that your head is constantly tilting left and right when you're reading, when you're doing anything, and you just don't even know it at all. There's no, it's just totally compensated, even though the image on the retina is getting wonky and twisted all around as you do this. So there's got to be a very ready mechanism for compensating for that kind of orientation change. And you think that this would be something that was discovered a long time ago, and animals started moving around because they move around. So it would be a sort of pretty fundamental mechanism to overcome these orientation differences. Now we're trying to extend it to complete objects, upside down and things like that.
Talking about animals, how old is evolutionary speaking the thalamus?
I don't know that. I don't know the answer to that question.
It's very tied in, at least in mammals, to the neocortex side.
Yeah.
I don't know,
Like birds.
have something.
Yeah.
What's funny with birds, they seem to have like more on a physical level a compensation for the body orientation. So they're very good at keeping their head really straight.
Well, I would argue the opposite. You know, birds, like you look at a pigeon, their heads are going back like, and I've heard people say like, how do they see? Aren't they going crazy? And I said to myself, no, the perception of the bird is the world is stable. It's the same like our eyes are moving all around, but we don't notice it. Doesn't bother us. And the chickens or the pigeon's heads going back and forth, they don't even see that. They just, the world seems stable to them. It's just like a saccade for them.
Is there a thalamus in the birds?
No, there's no regular cortex, although we've talked about this before. There seems to be pretty strong homologs between bird structures and cortical structures. So there's these blobs that seem to be like a section of cortex in some ways. So I think there's going to be very similar neural mechanisms going on, even though they don't have a cortex at all. But multiple people have made this analogy now. That, hey, these blobs, but literally call them blobs in some of these bird brains, that, hey, they look like they might be in similar to cortical structure. No, they're not a lamina sheet, they're just blobs. Anyway.
I was going to say, so the last bit of the kind of presentation is just to go through then sort of the patchwise representations, and in particular, this is an issue not just to kind of view spheres, but in general, if we've learned kind of nodes or kind of viewpoints, whatever you want to call them, and we have features associated with that, what happens when we sample at inference nodes that we're not familiar with, and how to kind of handle that. So this is just kind of an exploration.
Are you saying we're seeing the objects and we're seeing parts of the object we've never seen before, or we're
from
just
an angle that we've not seen before?
An angle we haven't seen before.
So, for example, you've primarily studied these kind of principal viewpoints, but you may not have seen it from a very particular angle. Or this could be.
But I'm not seeing new features. It's just a different orientation. Is that right?
Exactly. Yeah.
Okay, so that's. Yeah. Okay. I thought that's what we were talking about all along here.
But the thing is, when you learned the object, you'll have learned kind of features associated with certain viewpoints, but ultimately it's going to be kind of a semi-discrete representation of space, whether it's a grid mesh or it's a view sphere or even a 2D plane. But you need some way of kind of handling the continuous space between these sort of points where you actually kind of ascribe to memory a particular representation.
Okay, so this is like a mechanism for doing this. Is that right?
Yeah, so what I'm going to focus on is the feature representation and just how to maybe make that kind of robust or able to handle this.
Okay.
And because basically the desire is to, it's not plausible or desirable to learn every single possible orientation of an object. Sure, you might then be able to recognize it from any orientation, but it's just, memory-wise and kind of efficiency of learning, it doesn't make sense to do that. So this is basically saying how can we subsample the space and still generalize is the idea. And so we seem to be able to kind of do some sort of interpolation of features even for completely novel objects. I'm assuming you've never seen these particular objects before, but you can make a reasonable guess in your head of what you're going to see if I move these. It's not this, that wasn't what you probably predicted in your head. It was probably something more like this. So, the ring and the fur continue. You may have also predicted these kind of little bumps, that there would have been more of those. But yeah, the basic idea is, we can, even for novel objects, we can do a reasonable job just given a set of local features of predicting a nearby feature. And there's some work from DeepMind in 2018 where they were doing something that I think is kind of a related problem, where they had this room full of 3D objects, so a simulated room, and basically the agent received multiple viewpoints, so this view, and this view, say, and it would then learn to, given and with those viewpoints, it was also given their orientation. So it would get a view and an orientation, view and orientation, view and orientation, and then its task was to predict, given an arbitrary viewpoint in the room, what it would see from that angle. And it could learn to do this using a deep neural network. And so the idea was that it kind of developed a representation that was both invariant to particular orientations and able to process the particular orientation to give a particular viewpoint. And so the kind of thought is just that to learn kind of a long-term function that approximates, given a few local viewpoints, what you would see at an unknown point, and that this can then be used in conjunction with kind of temporal memory principles.
So on an experiment like this, there's two ways that, I don't know how the deep learning network does this. There's two ways.
Yep.
One way is you give it a very few set of images and it builds some internal model that allows it to rotate this stuff. Or you've given it a gazillion images and now your novel one is just a little bit different than the one it saw before. Which is it?
So yeah, it's probably a combination of both. So they did show some examples, for example, that this worked with objects it not seen before. And also it could generalize to some degree for different numbers of objects, for example, but it did eventually break.
It's more like how much training does it get, right?
I mean, I think a lot, yeah.
Right.
Yeah, I think it's in the millions of images.
Yeah, so then because we're trying to figure out a more mechanistic way of doing this, where there's these internal representations for orientation and location and so on, which we're pretty certain the brain is doing. But I generally think of deep learning networks as not having anything like that, although some practitioners will claim, oh, they're going to learn that stuff. But so it makes a real big difference. The example we use all the time here, so I've used many times, is you walk into a room and you see the arrangement of furniture, and then you leave the room, and then you approach the room from a different direction, and you can imagine what the room would look like, and you can recognize it right away. And it's like just a couple of presentations, and I can do that, or I can do it from a novel. I can imagine what a room looks like from the ceiling, and I've never seen it from the ceiling ever.
That's after you've been trained with millions of images.
No, I don't think so. I mean, my point is I can do this for very novel situations.
I'm saying that I don't think an infant has that capability.
Well, of course not. You have to learn, right?
No, that's what I'm saying.
Yeah, but I don't learn it by presenting me with millions of different. My point was I can learn this on a novel situation with from one direction. I don't have to be presented in lots of different directions. I just do it from one direction.
I wasn't saying that.
Okay, so I don't have millions of training.
I'm saying millions of training on
right. Let's
representing space.
So fine, let's just put it aside. There's a mechanism in the brain that's either learned or evolved. Doesn't really matter. Now I present this new thing it's never seen before. I give one presentation. I very quickly scan on it. Then I come from a completely different direction. I recognize that, and I can make predictions about it. So, I didn't do that by seeing millions of those rooms, right?
No, but he's saying I think he's saying that this thing can do that, but only to a limited extent, right?
Exactly. Yeah, it's much more limited and it's much more low level. It's what I'm kind of trying to show here. Like this is a completely novel object, but just given continuity of color, continuity of texture, continuity of edges, you're able to do a basic job of inferring what you're going to see. It has nothing to do with the fact that you're familiar with this object or how it changes. It just has to do with low level, essentially statistics of
It's funny,
of the visual world.
I would make an objection to this particular example, just to be clear. On the one on the left, I clearly envision it being a ring, and I know what rings are, and so if it was even slightly different from that ring, I would know it was wrong. On the one on the right, I can't make any predictions about the individual bumps and stuff in there. All I can do is basically sort of some sort of general. And if you show me a different arrangement of bumps, then that's where I would know it's wrong. So there's a difference,
Sure.
I think, in these.
But that's fine. I mean, so what I'm going to describe, it's fine if it was a different arrangement of bumps. What we don't want is for the predicted representation to be as meaningless as the smiley face. Like we want it to be something.
I'm just pointing. The one on the left is not based on statistics. The one on the left is based on the fact that I recognize a ring. If it was based on statistics, I might have just as well assumed that the brown fuzzy stuff is where the block
I mean,
is.
yeah, I don't argue against that. I mean, I think, yeah, I agree. I guess the problem is at some point we need to deal with the fact that we're sampling space discretely, and we need to kind of interpolate between it. And yeah, so I don't know.
I just think and I think about things like
it might be
careful. Yeah.
Yeah, so it may help if I kind of motivate a bit more what this is trying to do. So of course, this is kind of a coarse example, but just let's say when we studied it, we'd seen the teapot from the view of the handle and the view from the lid, and we'd memorized those and wrote those to memory. But now we're getting a view from this angle, and we're trying to, so we have the kind of pose, and we're trying to estimate what we're going to see there, because there is not going to be anything written to memory. And if we just try and use the nearest node that we do have in memory, that may not work that well. So here, obviously, this is very coarse that we just have a feature represented here and a feature represented here. Of course, we'd have some in between. But the point is that there are going to be many situations where we move off of the learned points and we want to estimate what's there. And so, for example, in this case, this is where we currently believe we are based on our kind of history of inputs. And we also in memory have this representation of the lid at this pose. And so the question is, how can we use this information together to make a kind of guess about what the view is going to be? And what I'm suggesting is to use a neural network, which is at the end of the day a function approximator, to essentially approximate, given these data points, so the views and the poses, both from memory and from our input history, as well as the pose of where we're going to be, to then estimate this possible viewpoint. And then when we move there, we can compare the internal estimate to what we actually experience. And that can give us some sense of, okay, we are actually at this query point, or actually, no, this is completely wrong. We're potentially on another object. But then the kind of key point then is, how do you train it to actually approximate this function? And I think what would be useful is to combine ideas from both, so contrastive semi-supervised learning, which is essentially what these top two terms are showing, and then a term that's a bit more like what that DeepMind paper was doing. So just to kind of break this down, so this is the loss function. So this is what the neural network is being trained through, say, backpropagation to minimize. And it has three terms. These gamma parameters are just scalars that determine kind of how much influence a particular term has on the whole equation. The first one, and yeah, simum is just a similarity measure, where the higher it is, the more similar two representations are. So for example, so for this first one, this is about getting the features to be invariant to noise. So this isn't actually about the interpolation question. This is just, the first two are about just having useful features generally, because interpolation isn't the only problem that they need to handle. So yeah, so basically what this is saying is that you get given a viewpoint and you perturb it in some way. You add Gaussian noise, you maybe flip it around kind of a mirror axis, or you change the color slightly. And basically you just want the representation to still be relatively similar and invariant. The second one is basically saying that you want representations of different features to be different. So if you take a viewpoint at one point and a completely random viewpoint, ideally from a different object, then those representations should be different feature space. Again, and sorry, yeah, just to clarify, so F is a neural network as well. And so this is after it's being transformed by the neural network, that the representation should be different. And then the last one is the key one for interpolation, which is you have this other neural network, which is kind of sitting on top of the first one. And it's taking these transformed features as well as their poses and potentially taking an arbitrary number, depending on how many you have to work with. So up to k representations, and then the query point, and then you want it to then give you, okay, what is the viewpoint at that? Yeah, what are you going to see at that viewpoint? And based on the history of papers in machine learning or kind of recent developments of the last few years, something like this should develop representations that can do a decent job of giving a few viewpoints from memory, as well as from what we're actually seeing, predicting what we'd see in an unknown space. And it could be interesting whether introducing sparsity into these representations could also help with making the kind of compositionality a bit more direct. So, of course, a handle and a lid are very different. So ideally, the representation that combines them and from that novel viewpoint would have both of those aspects. And so having sparsity may help with this. But I wonder whether we want to move away to some degree from SDRs and have real valued neurons, at least for this particular point, because having SDRs causes problems with gradients. You can't do gradient passes through binary representations. But so it could be kind of a mix of SDRs and real valued neurons. And so just kind of connecting this back to some of the early ideas. So the idea is that, the fact that humans have these preferred views could just be a parsimonious way of kind of capturing useful views without having to store all possible views in memory. And then this interpolation function could then handle more novel orientations. And it's important to say that, although this is all based on long-term learning and deep learning, this is still all dependent on path integration and rapid learning with Hebbian style feature representation. So it's a mixture of the two. And then, basically, as I said before, and then, at the neural level, if we're implementing this as kind of cortical columns, it may be that if you move somewhere and there are no known features based on the movement, then I don't know, maybe a lack of dendritic input initiates this kind of interpolation, which could be a more top-down feedback. And it's one thing that I haven't included in the kind of interpolation equation, but which might be interesting is sort of a global hypothesis about the particular object, which might also kind of constrain or kind of inform what you're going to see at a particular pose. And this might actually benefit from something like the continual learning dendrites paper approach, where you kind of have context applied to the neural network. I'm almost done. But just to say, the one difficulty of this is what happens if inference starts at an unfamiliar point, because what I've described works if we've visited nodes that we are familiar with and we're visiting one that we don't know. But it's not clear what we do if we start at an unfamiliar point. This is going to be most important for the first sensation. But what you could potentially do is sort of interpolate location. So basically, you're given your sensory input, and you have the stored features in memory, and you could find the k nearest features in feature space, and then basically interpolate the pose, weighing the contributions from each feature based on how similar they are. And if, for example, we're doing something like particle filters, then your estimated pose would be probabilistic. It wouldn't have to be just a single point. And this would, yeah, basically mean that you could, start doing path integration from a point on the sphere or point on a graph without having necessarily ever visited it before. I imagine this might be quite computationally slow to compare to all these possible features, but you would hopefully only have to do this for the very first sensation. And you could maybe have some sort of threshold. So it's only if the first sensation is very unfamiliar that you begin this process. If it's very familiar, then you just associate your location with the node that is associated with that familiar feature.
I'm missing something here. If I'm feeling something that's unfamiliar, why wouldn't I just move until I find something that's familiar? As opposed
You can
to
also do that. You
That
can also
seems
do
like-
that, yeah.
That seems like the simplest thing to do. Seems like,
Yeah, I mean, you can also do that, yeah.
Seems like what I would do.
But yeah, I guess sometimes it, yeah, I don't know. A lot of the, yeah, I think it'll just depend on how sensitive the features are. I think in practice to matching, whether that's, I don't know, and kind of how close you actually have to be for it to count as familiar.
That's true. There's always that question: how do you deal with variances? But as a general principle, it seems like if I see something that I don't understand, I keep looking around to find some part of it I do understand.
Yeah, no, that's true, and yeah, and that would avoid this slow.
Yeah, that
step.
seems like it mostly avoid this.
But yeah, so that's everything I wanted to talk about. So yeah, the next question is then whether we want to, at least for the HCM work, yeah, do something like view spheres and or planar views. But yeah, to my mind, still the planar views would be useful for translation invariance, but I think it'll require some form of kind of sphere-like coordinates in order to deal with rotation invariance. And yeah, that's everything. Thanks very much.